Good afternoon. Today is lecture number 7 in the course on laser-meta interaction, and today I would like to continue to talk about tensors and application of tensors in analysis of light-matter interaction. Imagine that we have measured circular bioregions. We know that circular bioregions is described by antisymmetric part of the dielectric permittivity. Also imagine that we would like to understand if these circular bioregions can be caused by an electric field. A very simple form of the expression that would describe this effect will look like this. Already here, we use the term tensor, because as I showed at the previous lecture, every quantity in physics can be represented in terms of tensors. Tensors will be of different rank. Number of indices next to an element of the tensor shows you the rank of tensor. For instance, this, what we would call normally matrix, would be tensor of second rank. This, what we would normally call vector, would be tensor of first rank. And this, chi, is a tensor of third rank. So we want to understand something about this tensor chi. This is third rank tensor. Again, as we showed at the previous lecture, all tensors can be divided into two groups: polar tensors and axial tensors. Polar tensors behave differently compared to axial tensors upon transformation of coordinate system. Any transformation of coordinate system can be expressed in terms of so-called generating matrix. For instance, generating matrix for such a transformation of coordinate system as space inversion, which practically means inverting direction of the axis in our coordinate system, will look like this. And for polar tensors, if you change coordinate system, the elements of the tensor in the new coordinate system will be found following a bit lengthy but still quite simple expression. For axial tensors, the expression will be slightly different. If you make sure that determinant of the generating matrix is either 1 or -1, so it is generating matrix from the very beginning is defined such that absolute value of determinant is 1, so it could be either 1 or determinant itself could be either 1 or -1, then the very same expression will be slightly corrected. In the sense that here we will have to multiply the result of this multiplication will have to multiply still also with determinant of the generating matrix. And in this particular case, it would be multiplication by -1. Well, looking at these two expressions and at the generating matrix for the operation of space inversion, we can see and confirm that polar and axial tensors do indeed transform differently upon space inversion, and this transformation depends on the rank of tensor. For instance, the zero-rank tensor, you can see, and you can look at the definition, at the rule of or the rule that defines the elements of tensor in a new coordinate system upon the space inversion. So you can see if you talk about zero-rank tensor, polar tensor, the components of polar tensor of zero rank will not change sign, but the components of axial tensor will change sign. If you talk about first-rank tensor, like classical electric field, for instance, which we know it is directed from positive charge to negative charge, and if you make space inversion in the new coordinate system, the vector will be pointing in the opposite direction. So then this vector will change sign because it's polar vector, and if it is axial vector, it will not change sign. And then and so on and so forth, depending on the rank of the tensor, it is either doesn't change, the components of the tensor either do not change sign if it is a polar tensor, or do change sign if it is axial tensor under operation of space inversion, or other way around. As you can see here, all polar tensors of odd rank are such that their components change sign under operation of space inversion, and all components of axial tensors of even rank are defined such that their components change sign upon operation of space inversion. Well, now it is an interesting question now, and a good exercise. Is it polar or axial tensor here in this expression? Let's analyze. Let's perform operation of space inversion and look how the elements in this equation change. Here it is very important to refer to our knowledge of physics. We know that in physics electric field is defined such that this is the polar tensors, and it is a first-rank tensor, and it changes sign upon operation of space inversion. Also in physics, epsilon is defined such that the elements of this tensor do not change sign under operation of space inversion. So you can see it's because it is polar tensor, because it is a tensor of even rank. And looking at this expression, you can see that if you want to satisfy this expression also in the new coordinate system, the components of this tensor chi should change sign under operation of space inversion, and it means that this is a polar third-rank tensor. That's how we define if it is polar or axial tensor. So in this particular case, it is a polar third-rank tensor. And we know that if we change coordinate system, in accordance with this generating matrix, in accordance with the operation of space inversion, the elements of this tensor should change sign. But if you look at the majority of all crystals around us, or all media around us, we will realize that majority of all media, condensed matter media around us, are crystals. And it happens because regular position of atoms appears to be more energetically ferrable, energetically more ferrable than irregular position of atoms. Well, let's look, for instance, at the crystals, and imagine that we take a very simple crystal with a cubic elementary cell, and this crystal consists of just one type of atoms. And for this crystal, we can choose, obviously, we can choose a point such that if we place the center of the coordinate system exactly at this point, and if we try to define the coordinates of all the atoms in this coordinate system, we will understand, we will see that if there is an atom with coordinates x, y, z, there will be also atom with the coordinates minus x, minus y, minus z, because this is basically the property of a cubic crystal, of a cubic arrangement of atoms. In this case, we will call such a crystal or medium with this property in general centrosymmetric medium. So basically, everything what we find with coordinates in this crystal x, y, z can be also found, the very same feature will be also found, but with coordinates minus x, minus y, minus z. Well, imagine now that if you talk about centrosymmetric medium, and if you try to define the element of this tensor, obviously this tensor component will be defined by coordinates of all atoms in the crystal. Huge number of atoms, so imagine we found a function that depends on position of all these atoms. And now you make space inversion. After you make space inversion of each atom with coordinates 1, z would be substituted for an atom minus 1 minus y1 minus z1. Well, then similar function will be can be also written for elements in the old coordinate system, and what you will see that since the crystal is centrosymmetric, we will practically have the very same set of atoms here and the very same set of atoms here, and for this reason we should state that since the crystal is centrosymmetric, obviously all the properties should be invariant with respect to space inversion, and it would mean that if you make operation of space inversion, the elements of the tensor will not change. And here we have a contradiction. While mathematics of transformation of elements of tensor upon space inversion tells us that upon space inversion tensor elements should change their sign, logic tells us that if we talk about centrosymmetric media, space inversion cannot affect the properties of media, and for this reason tensor elements are not allowed to change sign. The only way to resolve this contradiction is to assign all elements of this tensor to 0. What it tells us that if you look at the original table, which I have just drawn, these are polar tensors, axial tensors, this is rank 0, 1, 2, 3, 4, plus, minus, plus, minus, plus, and here minus, plus, minus, plus, minus. This tells us that properties which are described in centrosymmetric media by polar tensors of odd rank and axial tensors of even rank are simply forbidden. They are not allowed by symmetry. if you talk about centrosymmetric media, properties which are described by polar tensors of odd rank and axial tensors of even rank are forbidden. And for this reason, looking at this expression, you can say that electric field can induce antisymmetric part of the dielectric permittivity and, as a result of it, also circular bioregions, only in non-centrosymmetric media, in media which do not have a center of symmetry. Also, similarly, last lecture I tried to apply the operation of time reversal, and again, if you apply operation of time reversal and do a very similar trick, you understand that antisymmetric part of the dielectric permittivity is defined such that its components change sign upon time reversal. Electric field doesn't change sign upon time reversal. It means that components of this tensor must change sign upon time reversal, and it actually says that this property, or in particular antisymmetric part of the dielectric permittivity induced by the electric field, is only allowed in media which are sensitive to time reversal. The properties of this media must depend on quantity which is sensitive to time reversal. And these quantities are magnetic field, magnetization, speed, angular momentum, current, whatever associated with motion. And here we arrive to a very important principle in physics, which is called Newman's principle, and very similar to this principle, another formulation of very similar statement is called Curie's law. Any type of symmetry which is exhibited by the point group of a crystal is possessed by every physical property of the crystal. Or similarly, in the formulation of Curie, when certain effects show a certain asymmetry, this asymmetry must be found in causes which gave rise to them. What does it mean? It means that if you have a crystal with a certain crystal structure, and if you go along one direction and you might find one type of atoms arranged in one way, and if you go in another direction, you find the very same type of atoms arranged in the very same way, then there is no reason to claim that the properties of medium in this direction would be different than the properties of this medium in this direction. So these directions are crystallographically equivalent, and it means that physically they must be also equivalent. More particularly from the point of view of light-matter interaction. So light will fall on this medium with electric field. It will excite electrons here, and different polarization of light, of course, will excite different oscillations of electrons. For instance, if the polarization is in this direction, it will excite electrons oscillating in this direction. And if the polarization is along this direction, the electrons would be oscillating in this direction. Of course, while oscillating, they will feel local environment. And if arrangement of atoms in this direction is absolutely equivalent to the arrangement of atoms in this direction, there is no reason to expect that optical properties shown by media during the interaction with light with this polarization will be different than optical properties for light polarized in this direction. So basically, what I wanted to say here is that if you observe something asymmetric in the experiment, asymmetry must have a reason. However, if you talk about asymmetric medium, imagine that here we have rather different directions. It doesn't mean that by law you always have to observe this asymmetry experimentally, or simply because it could be that our experimental setup is not sensitive enough to see this difference. So it is only asymmetry must have a reason. But be careful with applying this law it doesn't mean that if you work with asymmetric media, the property that you observe must be asymmetric. Well, and this law has far-reaching consequences for defining the elements of tensors, because we actually can use the very same trick as we have used before, before we apply this trick to the operations of time reversal and space inversion. But now, if you talk about crystals, we have many more operations of symmetry. Next to center of symmetry, when an object has a center of symmetry such that if every point at the position x, y, z relative to the center is also found at minus x minus y minus z, so in this case we will call it centrosymmetric medium. But we can also have rotational n-fold symmetry, which is present if an object comes into coincidence with itself after rotation by an angle 360 degrees divided by n. For instance, two-fold symmetry means rotation over 180 degrees. And in this case, you should imagine the following situation that we have, for instance, a crystal lattice. You rotate the crystal lattice over 180 degrees, and you cannot say how many times you have rotated this over 180 degrees. You see the very same crystal always. They say another symmetry operation is a mirror plane, such that you can imagine that there are two parts of the crystal. You can place a plane and the upper part of the crystal reproduce exactly the lower part of the crystal. And there is also rota inversion n-fold symmetry, is a more complex element. It's a symmetry operation of rota inversion, is a two-stage process. First, it is the operation of rotation symmetry, and this is followed by second operation of reflection through a center. Good thing that despite that it's very difficult to imagine all these symmetry operations, and especially if you look at the very specific crystal structures, it is difficult to find out all these symmetry operations. Good thing that it has been done already before. Combination of different symmetry operations in 3 dimensions will form 32 different combinations, and these combinations are actually 32 crystallographic so-called point groups. These point groups are shown on this slide. As you can see that the top point group is the most symmetric one, so it contains most of symmetry elements, and the lowest point group is the least symmetric one. So you can also see that adding particular symmetry operations, you can come to from the least symmetric point group to the most symmetric point group. And again, good thing that we don't need to learn all these by heart. We just have to be aware that these point groups exist. So if you talk about particular crystal, every crystal has a point group, and this point group has been defined already. For every point group, we have also in the tables the list of all symmetry operations that this point group allows. And, well, in this particular case, for instance, in the particular case of gallium arsenide and silicon, the point groups are well defined. We just look at the table. We first look in the textbooks, define the point group of the crystal structure. Then we'll look in the tables, like in this book, where for particular notation of point group, by the way, be aware that there are different notations of point groups. But once you define point group, you can define the symmetry operations, and this is in the 6th column in this table. And again, for every symmetry operation, there is a corresponding change of the coordinate system. And for every change of the coordinate system which is allowed by this point group, by the symmetry operation of this point group, we have already generating matrix defined. It's all in the books. We don't need to derive anything. Here, for every 32 point groups, everything is brought into tables. Generating matrices that you will find in these tables are also given, for instance, like on this slide. For every symmetry operation, you can find a generating matrix. And if you want to say something about the elements of this tensor, we now have to use this. We now can use this knowledge of the point groups and see maybe we can simplify the situation and say something already in advance about the elements of this tensor in particular. Yeah? So if you start with just with this tensor, it will have 27 independent components. However, not all of them are non-zero. Well, what we have to do to define number of non-zero tensor components, we have to look at the tensor and define if it is a polar or axial tensor in the way I did just at the beginning of the lecture. Once you defined that this is, for instance, a polar tensor, you choose one symmetry operation, which is allowed by this point group, and use the generated matrix for this operation to transform the coordinate system accordingly. You find the elements of this tensor in the new coordinate system. And if from the symmetry operation, from the change of the coordinate system, it follows that in the element in the old coordinate system must be equal to the element in the new coordinate system with inverted sign. At the same time, the definition of the symmetry operation is such that if you do this, if you form this symmetry operation, you will find the very same crystal. So logic tells us that elements of the tensor shouldn't change sign. And again, in order to resolve the relation between tensor elements in the new coordinate system and the old coordinate system, which we found mathematically, and logical conclusion that if this is a symmetry element, you perform if you perform the change of this coordinate system in accordance with this element, the properties shouldn't change. The only way to resolve this contradiction is to assign all these elements with this contradiction to 0. This is how we define zero tensor components, and this would be a topic at one of the exercises at the lecture. So, for instance, if you look at the real tensors for a particular point group, like very symmetric point group, you will see that there are very few mutually independent tensor components. You can reduce number of independent tensor components substantially if you use these tools of symmetry and applying generating matrices and checking if the elements of the tensors change and how they change upon the change of the coordinate system in accordance with a particular symmetry element. And we know that the symmetry element is defined such that the crystal shouldn't change. That's why we bring these two statements in contradiction and assign a particular tensor components to 0. Okay, so I hope this explains a little bit how we can work with tensors. And I would like to come to the next point. I would like to dream a little bit now and think about a phenomenon which would be defined in the frequency domain by an expression like this, where E is the electric field of light, this is some tensor, and here is the polarization induced by these two electric fields of light. So already from here you can see that what I do, I assume that the dependence between the electric field of light and the polarization is nonlinear. So I would like to make the first step towards nonlinear optics. Well, if you now put a very simple expression for the electric field of light. We ignore here dependence on the coordinates, we just take into account dependence on time. And if you find a product of two electric fields, you will see that this product gives me something that changes in the frequency to omega and something that doesn't change at all. So basically the response here would be at the frequency to omega and also at the frequency 0. What it means? It means that if you take into account this dependence of the polarization on the electric field of light, the polarization induced by the electric field will not be anymore at the frequency omega. The frequency will be changed. And it would mean that if you send light at the frequency omega to the crystal, you will induce polarization at the frequency 2 omega and at the frequency 0. And if there is polarization at the frequency 0, if you put here electric contacts, you will be able to measure voltage. And if you induce here polarization at the frequency 2 omega, it means you will, in accordance with the wave equation, you will induce electric field at the frequency 2 omega, and it means that the emitted light would be at the different frequency, 2 omega. So for instance, if you send here light with a wavelength of 600 nanometer, which corresponds to red light, the wavelength of light coming out would be 300 nanometers. It would be blue or even close to ultraviolet. So the color of light will change. And this phenomenon is called nonlinear optics. By the way, the effect of doubling of frequency is called second harmonic generation, and the effect that you induce polarization at 0 frequency while pumping with electric field at omega, we will call optical rectification. What people do to simplify it, to simplify notation and to distinguish these two processes, they actually limit themselves to this definition of the electric field. And in this case, second harmonic generation would be written would be described by this expression: an optical rectification will be described by an expression like this. So now we arrive to another chapter of this course, which is called nonlinear optics. Well, let me summarize what we expect from linear optics. In linear optics, properties of medium do not depend on light intensity. So it means that it doesn't matter how much intensity you put on the medium doesn't change its properties. So that epsilon doesn't change, refraction coefficient doesn't change, chi, optical susceptibility doesn't change. It simply doesn't depend on intensity. Principle of superposition holds. So it means that if you have an interference of two waves, it will always, these two waves will always interfere in accordance with the principle of superposition. The frequency of light cannot change upon interaction with a medium. So basically here, if you assumed linear dependence between electric fields of light and the polarization induced by this electric field, there is no way to change the frequency of light upon interaction with medium. And as a matter of fact, also light cannot interact with light. If one of these principles is violated, light-matter interaction can be treated as a nonlinear process. And in this particular case, we see an example of changing of frequency of light upon interaction with medium. The very first observation of nonlinear optical phenomena is the paper reporting about very first observation of one of the very first observations, let's put like this, of optical phenomena, in particular very first observation of second harmonic generation, shown by this expression. It was reported in this paper, and there is also anecdote associated with this publication. So you can see here an experimental setup which was used by people to observe the phenomenon of second harmonic generation. First of all, in order to observe second harmonic generation, they needed lasers because they needed strong electric fields, because only having strong enough electric fields they were able to detect next term in Taylor series, in Taylor expansion of the polarization with respect to electric field of light. Then they shine this light on the sample, and then they put prism, expecting that light at the frequency omega, which will be the majority of light coming after the sample, will be refracted in one way, and there is a very small part at the frequency 2 omega, then it would be refracted in a different way. And they put the photographic plate behind this prism, and they made a photography, and they found, of course, very large, very intense spot that would correspond to a signal at the frequency omega, obviously because the first term in Taylor expansion is much larger than the second term, and then they found very tiny spot that corresponded at that time to a signal at the frequency 2 omega. And at that time, in 60s, the papers were, of course, submitted to journals, not in a digital form, but by post. And in this particular case, they simply sent a photography of these two spots. And the editor, when the paper was eventually accepted and prepared for publication, thought that this very small spot is just a defect in photographic image, and it was removed in the final paper. And in this way, you can see that the arrow shows where the signal should be, but the actual signal is not there. So the very first report about second harmonic generation was published without showing actual data. Now it's very interesting also to think about this tensor for the case of second harmonic generation. Is it a polar or axial tensor? So let's do the trick which we have done already several times at this lecture and at the previous lecture. We know that polarization is a polar vector. It will change sign upon space inversion. Electric field is a polar vector of first rank. It will change sign upon space inversion. And looking at this expression, we see that the elements of this tensor should also change sign upon space inversion. And this is a third rank tensor, so it means that it is a polar tensor. It is a polar tensor of odd rank, and the properties which are described by this tensor are only non-zero in non-centrally symmetric media. So basically, if you want to observe second harmonic generation, you should take a non-centrally symmetric medium, exactly as it was done in that paper. You can see here a nonlinear crystal was put in the experimental setup to observe second harmonic generation. But also, second harmonic generation can be observed from centrosymmetric media, particular from interfaces of centrosymmetric media. Imagine that we take a silicon, which is a centrosymmetric crystal, and here we put silicon in the vacuum. In vacuum, you can also say it's a centrosymmetric medium. And if you look here, in the bulk of the crystal is centrosymmetric. If you look here in vacuum, it is centrosymmetric. But here at the interface, for very few layers of silicon, the center of symmetry is broken, and it means that second harmonic generation must be allowed at the surface. And this trick was used in this paper shown on the slide, where they actually measured second harmonic generation from the surface of silicon, and more particularly using symmetry analysis of the tensor responsible for the second harmonic generation, they were able to find that number of independent tensor components for this tensor is not that large. So if you rotate polarization, not at every polarization of light, not at every electric field of light, polarization at the second harmonic will be non-zero. And they use this fact to define symmetry of the surface. In particular, they were able to define, they were able to reveal how the symmetry of the surface changes in time. And so-called surface reconstruction was observed. So this brings me to conclusions. Tensors, together with the knowledge of point groups and Newman's principle, are very powerful tools in theory of light-matter interaction. In particular, based on this knowledge, one can use nonlinear optical phenomena as a prop of crystal structure, as I showed you at the very last slide. Even if the wavelength of light is much larger than the atomic distances in the crystal lattice, it is still possible. And why? Again, you will be able to see it doing exercises. Thank you very much.